7.5 conic sections. So we're looking at a cone over here. They're making a point that a cone has two napes. This is a nape. Two napes form a cone. Take a plane, sheet of paper, and place the plane so that it's parallel with this line. Then that sheet of paper will intersect with the cone in only one of the two napes. Here it's shown intersecting with the top nape. Take the sheet of paper and tilt it down so it's horizontal. Now the cross section will result in a circle. Let that sheet of paper go from being horizontal to now tilting down, but not creating an angle parallel to this line. As in this picture, we're getting a cross section which is an ellipse. You want to think of a circle as a special case of an ellipse, not a separate conic. Take the sheet of paper and let the sheet of paper be parallel with the axis of symmetry of the cone, and consider the cross section created with the two napes, and you will result in a hyperbola. The conic sections that we'll consider, there are three of them: parabolas, ellipses, and hyperbolas. Very good. Let's start first with a parabola. We've seen visual pictures of what a conic is, in particular parabola. Here is a definition. Let's read over the definition. So parabola is a set of points. What points do we want to consider? We want to consider points in the plane, x comma y, a point in the plane, that satisfy being equidistant from a fixed point, that point we'll call a focus, and a line, a fixed line, that doesn't contain the focus, called the directrix. All right, let's look at a picture to familiarize ourselves with this vocabulary, focus and directrix. So we have this picture over here. Let's zoom in on that picture. And then we have a familiar parabola. We're familiar with what parabolas look like. And they've picked a point on the parabola. And then they're taking a distance from that point to a fixed point. This is called the focus. So this point here, that's called the focus of the parabola. You're familiar with the vertex of a parabola, with the axis of symmetry of a parabola. The vertex and the focus lie both on the axis of symmetry. Here in this case, our parabola is opening up. Go to the other side of the parabola and draw a line which is perpendicular with the axis of symmetry. Draw that line such that every point on the parabola has a distance to the focus and a distance to this line, called the directrix, which are the same, d. Now, you can take P to be the vertex, and so the distance from the vertex to the focus and the distance from the vertex to the directrix is going to be the same. So if we allow our focus to be P away from the vertex, then the directrix will lie P below, in this case, the vertex. And we can see that in this particular picture, we're taking the vertex to be at the origin, so that the focus here will lie on the y-axis with coordinates 0, p. Then this horizontal line, well, what's true about this horizontal line? It has all y values the same. And if the focus is at 0, p, then this point here would be 0, negative p. Hence, the directrix is given by the equation y equals negative p. All right, so we've learned some vocabulary, a focus and a directrix. And let's go back and look one more time at this definition. A parabola is the set of all points whose distance from the fixed point, which we know is called a focus, is equal to the distance from a fixed line. That fixed line we call a directrix. The halfway point between the focus and the directrix is called the vertex of the parabola. Very good. Okay, so we have seen, let me scroll back up, a visual idea of what a parabola is, and that we are taking a cone and we're finding just a piece of it, hence the name conic section. So that's one. And then two, we have this idea in terms of a set, in terms of finding points which satisfy some condition. So next, what we're going to do is we're going to take this definition and come up with algebra, an equation to describe the parabola. So let's go through this. Now, we have here, let's copy this down. We have here this notation of d. So in this case, they're going to use d as a function. And a function needs to take input. And for this function, we need 2 points, a point P and a point Q. And hopefully you guessed that D is representing the distance. Then we're going to need for the point P and for the point Q to have coordinates to be a point in the plane. So let's take the P first and let it have coordinate x. But we know that the Q is also going to have a coordinate x. So let's call the x coordinate on P, let's call that x1, and the x coordinate for Q to be x2. So then we'd get y1 and then y2. All right, and then you want to know the distance formula. It's essentially just the Pythagorean theorem. That you want to look at the difference of the two x values, so x1 minus x2. They've written it out as x2 minus x1. It doesn't matter since we're squaring this quantity. And then I've gone x1 minus x2, so I'm going to also go y1 minus y2. And again, you can call that y2 minus y1. It doesn't matter. Okay. So here we've just recalled the distance formula, given a point P and given a point Q. Next, we want to apply that distance formula to our picture. And what they do on one side is they take the focus, which has nice coordinates 0, P, and they look how far is the focus from a point P. And here we need to keep in mind that in this picture, the focus is fixed. The directrix is fixed. The parabola is fixed, but what we want to consider on the parabola is an arbitrary point. So this guy here can be anything. We know that because we're allowing the coordinates x and y to be anything. And to represent that, we leave it as variable x and variable y. Then that point is only going to be on the parabola if this distance and that distance are the same. That's the idea. All right, so here's the distance formula. Let's apply the distance formula here by taking P to be F and Q to be P, where P is given by x, y. So let's put a highlight down. Take this, let it be that. So then P, we're going to let that be F. So this will be 0, lowercase p. And then Q, we're going to let that be the point P. So that will have coordinates x, y. So then we take these and update our formula, and we should get this. So let's check. X1 would be 0, and indeed we get 0. And then x2 would be x, and indeed we get x in the formula. Let's check the other piece here. For y1, I have lowercase p, and the book gets lowercase p as well. For y2, I have y, and the book has y as well. Okay, very good. Nice and easy. Then you do the same thing where you take the distance from P to Q, the distance from P to Q. So what are they doing for Q? Well, they want that to be this guy here. So what is Q? Q is the point on the directrix that corresponds with point P, and it gives you the distance from P to the directrix. So if we were to move P, say, over to here, then we would want to look straight down. In other words, we want to be forming a right angle here. So if that's going to be true, then both P and Q will share a first coordinate x. But we want Q to be on the directrix. What's the equation of the directrix? Y equals negative P. Hence, the y coordinate on Q must be negative P. Okay, so we have already D expressed out here. And now we're trying to express out D for the distance between P and Q. And let's verify. We get x minus x, that's x minus x. And then we get negative P minus y, negative P minus y. Very good. So we have this equaling that. Okay, how about we copy that down? So when we copy that down, I'm just copying here. I'm going to get negative 0 minus x quantity squared. I'm going to write that as x squared. So I did a little bit of work there. And the next one, I'm going to call that 0 squared, or 0, I'm going to ignore it. Okay. Now, if we have this radical equaling that radical, then it must be the case that the radicands, namely everything underneath the radical, are the same. So we can simply get rid of that radical. Square both sides. Next, what we want to do is we want to expand these powers of 2. Copy the x squared, p squared minus 2py plus y squared must equal. Expand on the right-hand side, negative p times negative p is p squared. Negative p times negative y is positive py. Get that twice. 2py and then plus y squared. And then you go through and you say, well, I have a p squared here, p squared there, I have a y squared, I have a y squared. They'll cancel out. And then I'm able to collect this with that and come up with this equation, which we can write down. X squared equals 4py. And that's it. We're done. That is how x and y need to relate. And you can divide through by 4p. 4p is a constant. You get y equals something times x squared. Y equals x squared is a familiar parabola. So what have we gained? What have we benefited from? Well, if we fix a focus, then that means we're fixing a p. And then this is how the x's and y's must relate. Okay. And then you get 4 different versions. We had fixed our vertex at the origin. If you allow, let me zoom in there. If you allow for the vertex to be anywhere, well, what does h do? H changes the x. So remember, it was x squared. It was 4py equals x squared. So if you change x by h, then that x squared becomes quantity x minus h squared. Then if you want to change your y, you have to change your y by looking at y as y minus k. So that would be y minus k equals 4p x minus h quantity squared. Then take the minus y and plus it to the other side. And that would give you 4py, so then divide through by 4p. Alrighty. And then accounting for p to be negative, you would get a parabola that opens down, hence you have that minus there. If you just interchange x's and y's, then the parabola will open either to the right or to the left. And you can look at the equations and see that the equations simply have x's and y's swapped. And when you swap x's and y's, you need to carry along with it the k or the h. Very good. So that's parabolas. The other type of conic, or another type of conic discussed in chapter 7, is an ellipse. So I disagree with the book in that it takes a circle as a separate conic. Treat circles as a special ellipse. A circle is an ellipse. All right. Let's go ahead and copy this picture that we're looking at over here. Let's bring in the x-axis. Take the y-axis. And then let's mark out the center. Let's give that a blue point. That's the center. They call it O for origin. Then let's go here and here, the vertices. Let's go over there and over there. And we can see that from the y-axis, we want to move A to the left and move A to the right. So I'll call that x as negative A and x as positive A. So there's an A and then here's a B. Let's do the same thing. Let's pick off a B and a B. So positive B and negative B. And then eyeball in the shape. So let's do that. Sketch in roughly. An ellipse. And then next, let's go to these guys. That's F like before, the foci. And on the foci, we have that that's occurring a distance c from the center. Okay. Good. So we have an F and we have an F prime, another one. We have a P for a vertex and then another vertex P prime. And then we have a Q and a Q prime. All right, and in this picture, you want to note that in this picture, A is bigger than or equal B. So in the case where the A and the B, where A and B are actually equal, that would be the case of the ellipse turning into a circle. But when we're talking about ellipses proper, then we want to introduce this notion of a foci. And then that's going to occur on the axis where the A's are. And this is termed the major axis. Let's write that phrase down. Major axis. Versus in the other case, the y-axis in here, that would be the minor axis. Okay, good. All right, now with that, let's go read the definition of an ellipse. And again, we're trying to identify points in the plane. So all points, what do they need to do? We want the points to have a distance to the foci, which is constant. Right? Let me rephrase that. Let's just go ahead and read. An ellipse is the set of all points for which the sum of their distances from two fixed points, called the foci, is constant. So let's go ahead and add into our picture an arbitrary point. Let's go with a pink point. There's a point. P. It's arbitrary, so let's give it coordinates x, y. And then let's draw in the distance. So from the point P to F1, or F prime, let's call that D1. And from the point to F, and we'll call that D2. So we can see, unlike the parabola where the distances were equal, now what they're saying in this definition, we have a D1 and a D2, that the sum D1 and D2 needs to be constant. That's the definition. All right, let's play around with that. And what they do is they begin by considering this distance for and this distance. So let's go ahead and mark in the picture that they provide. P to F, and they're taking P to be this point here. Okay. So if we mark that out and we look at P to F, that would be this here, that distance. We know that this measures A and that this measures C, and so that's how we get A minus C. That the distance from P to F, from P to F, is all of A, take away C, so A minus C. All right. So if we take that point, we can look to one focus, and then we can look to the other focus. And we can see to the other focus, we have all of A that needs to be covered, all of A. And then this distance here is C, and that's how we get A plus C. Okay. All right, so again, this point, how far is it to one focus? A minus C. This point, how far is it to the other focus? A plus C. And then when you do simple arithmetic, A plus A gives you 2A, and negative C plus C gives you 0. So you get 2A, telling us that, go back and look at the previous page, that D1 plus D2 equals a constant, and the constant is 2A. Fantastic. So what did we do? We used this vertex to come up with the constant must be fixed at 2A. So therefore, we can go in and plug in the distance from any point A to the focus F plus the distance from any point A to F prime must be twice A. That's what we have. Very good. So recall that F had coordinates 0, C. F prime has coordinates 0, negative C. And then that's how we get this next line here. And any point is our arbitrary point, x, y. So that when we look here, from this point to that point, we're going to get x minus 0, that's x quantity squared, plus y minus c quantity squared. Oh, my bad. I have these backwards. C and 0, negative c and 0. since we have a major which is horizontal, not vertical. Okay, x minus c quantity squared. So x minus c quantity squared and then plus y minus 0 or y squared. Add to that the distance between a and f prime. X minus negative c is x plus c. And again, y minus 0 is y squared. All right, let's continue on with this. Let's go ahead and move. Let's move one of the radicals to the other side. So move the second radical to the other side. Have to subtract it. And now we have one radical isolated so that we can remove this radical by squaring both sides. Two a times 2a is 4a squared. Get 2a times that radical 2 times, so negative 4a, and then the radical. And then the radical times itself will remove the radical and leave you with the radicand. Can do a quick observation that y squared appears on both sides. This is the sum, this is a difference, so we need to multiply those out. If we multiply out, we get x squared minus 2cx plus c squared. If we multiply out on the other side, we get x squared plus 2cx plus c squared. And then we can observe that x squared appears on both sides and c squared appears on both sides. All right, clean that up. We'll be left with negative 2cx, and let's go ahead and combine that with positive 2cx. And if we do that, we'll be left with a 0 on the left. Copy the first two terms on the right. And then we've added these guys together, combine them. Get that. And then you can notice that there is a 4 appearing in each term, so you can divide through both sides by 4, canceling out the 4. Next, let's see. Let's do the same thing. Let's concentrate on that term there with the radical. So let's add it to the other side. So I've moved this term to the other side. Then I'm left with, on the right-hand side, an a squared and a cx. And just to keep things simple, let's divide through by a. And dividing through by a, leave you just with the radical on the left-hand side, and on the right-hand side we'll get an a and then a c over a on x. So now that we just have the radical all by itself on the left-hand side, we'll square both sides. Left-hand side, we're just going to get the radicand. And the right-hand side, we have two terms that are being multiplied together. That'll give a squared. When you take a times c over a, that gives you c. So we'll get twice cx. And then c over a times itself is c squared over a squared on x times x. Again, expand out on the left-hand side to get x squared plus 2cx plus c squared. And then observe that you have 2cx appearing on both sides. And then let's go ahead and combine terms. So I can notice that there's an x squared term and an x squared term, and then a constant and a constant. So I'll bring the constants to the right, and then the x squared terms. Since there's an x squared with coefficient 1 and an x squared I'm going to subtract over with this coefficient, I'm going to end up with 1 minus that coefficient. 1 minus that coefficient, all of that is on x squared. Now, if I rewrite 1 as a squared over a squared, I can then combine these terms and find that I get a squared minus c squared over a squared on x squared. Oh, and I forgot to copy the y squared down. Alrighty. So then let's go ahead and divide through by this quantity. Dividing through each term by this quantity will leave us with x squared over a squared. We want to divide every term by that quantity, so we'll get y squared over that. And then the right-hand side is exactly that quantity, so we're going to get something equaling 1. And that's very nice, coming up with 1. But we have this really odd-looking a squared minus c squared. So let's go back to our picture. Let's go back to our picture. And in particular, let's take this guy here. So let's copy some of that. We have the center. Then we have a point up here, b away from the center. Point over here, b below the center. We have the vertex and the vertex. Those are a away. And then we have a focus and a focus. Those are c away. So here's c, a, and b. But we know that this is a point on the ellipse. So when we look at the distance from that point to the focus and to the other focus, we know that this sum, d1 plus d2, is going to equal 2a. But hopefully you would agree that that and that are the same length, so it must be that a plus a equals 2a. So we get that hypotenuse there is a, and it's a hypotenuse to a right triangle with side of height b and base of length c. So that's b. Let me change the color. Easier to see, b and c. Very good. So the Pythagorean theorem tells us that b squared plus c squared is equal to a squared. Looks pretty funny. But that's exactly the Pythagorean theorem applied to this right triangle. All right, let's manipulate this. Let's solve for b squared. And that should be familiar there. A squared minus c squared is b squared. Let's go ahead and plug that back in. So a squared minus c squared is b squared. So copy that down. First term unchanged. Second term has an updated denominator, b squared. Right-hand side, all good. Okay, nice. Let's go ahead. This is just all the computations that we've done already. So here's what we just did. Oh, we're ahead of that even. Here we go. Here's what we just did. We were at that form, and then we were able to find that a squared minus c squared takes the form of b squared. Oh, the book. Poor book. Lots and lots of typos. A squared minus c squared is b squared, and so we've come up with a nice form. Let's review. X-axis, y-axis. We've assumed that we're going to take a center at the origin. Move away A. That's going to give you the vertices. Move away C, smaller than A. Move away C, smaller than A. Take B. B is smaller than A. B, smaller than A. And then get an ellipse. That here we have a major axis. So that when you look at this equation, note that for an ellipse, it's always going to be a sum here, and that the A quantity will always be the bigger value than the B. So if above the A you have X, the major is horizontal. Let's write that out again. Let's draw another ellipse, but where the major is instead vertical. Something like that, very crude drawing. Then over here we'd have an A, a negative A, a B, a negative B. And then this ellipse would take the form y squared over a squared plus x squared over b squared equals 1. All right. So note, when x squared is appearing over the A, the large value, that you get a major, which is horizontal. However, you look in the bottom, find the larger bottom, look at the top, what variable do you have? If it's a y, then the major is going to be vertical. Very easy. Excellent. So then go ahead and look at these guys here. Note that you have 1, 2, depending on a major being horizontal or the major being vertical. And again, you simply look at the A, look at the top. Is that an X or Y? That tells you whether it's horizontal or vertical for the major. And then the H and the K, that's denoting the center. Fantastic. Hyperbolas. Hyperbola is very, very similar to the ellipse with some differences, of course. Let's start by reading the definition. So again, a hyperbola, we want to describe it in terms of sets of points in the plane. Oh, and here's where a big difference is. If it was an ellipse, that word there, instead of difference, would be a sum. So now we want to consider the difference between the distances from the point to the foci. We want that to be constant. So now when we have the distance and the other distance of a point to a foci and a point to a foci, we want to consider the distance, and we want this to be constant. So again, on the ellipse, that would be a sum rather than a difference. Now sometimes this will be smaller than that, leading to a negative quantity, which is not the same constant. And the way that you work around that is you put absolute values. All right. Now, starting with that definition there, as we have written in purple, you can follow. We'll come back to that in 1 second. You can follow all of the algebra, and it's very, very similar. And let's see if we have it. Yep. And the only real difference is that you're going to get here, instead of a sum as you had in an ellipse, you get a difference. You get a difference. All right, let's go back to the picture and make some notes, some comments. Let's go ahead and copy the picture. Easier that way. So let's start with the XY axis. And again, we want to place the center at the origin. And we want to go find the two foci. Let's go way over here, and note that they're sitting inside what look like parabolas. And that should be familiar. Let's go ahead and label that F and F prime. And then let's bring in the vertices here and here. Then draw a couple parabolas, one opening left, one opening right. Something like that. Open to the right, open to the left. And then let's recall that we are using the letter C to indicate the distance to a focus, and we're using the letter A to indicate the distance from the center to a vertex. All right. So note that here now the A is going to be smaller than C. A is smaller than C. And then the quantity B, well, you might recall, you might have learned about the fundamental rectangle. If we find the B and draw in this fundamental rectangle, so my picture is not great at all, that what you would find the fundamental rectangle satisfies gives you diagonals which happen to be asymptotes for the hyperbola. The hyperbola wants to tend towards those diagonals on the fundamental rectangle. Let's look at the book's picture. Here we have the diagonal. And then we have this guy here, the fundamental rectangle. Fundamental rectangle is going to determine our value of B. Alrighty. Okay, so we had a major axis where the vertices and the foci lie in terms of the ellipse. For a hyperbola, that major axis has a new name. It's called the transverse axis. The minor axis gets called the conjugate axis. Excellent. Okay. Now, the A, B, and C for the ellipse satisfy a funny equation, but for a hyperbola, the A, B, and C satisfy what looks like a familiar equation, the Pythagorean theorem, a squared plus b squared equals c squared. The other thing to comment is these two equations, how can we glance at them and quickly know whether the the transverse axis is horizontal or vertical? All right, well, that's pretty easy. So the equation in standard form for a hyperbola is a difference set equal to 1. And this term is something squared, and this term is something squared. So on the left, you have a difference of a square and a square. Then if it's a hyperbola, it'll be set equal to 1 if it's written in standard form. Then the first term, where the minus does not appear, will always have a denominator a, given in a squared. So once again, you simply have to look at the variable appearing in the numerator, and if that variable is x, then the major, or the transverse axis, will be horizontal. Whereas when you look at the difference, set equal to +1, the first term will provide you with a in the bottom, and in the top, if you find the variable y, then the transverse axis will be vertical. Excellent. So let's see, the other thing to note is that the relation between a and b, well, there is none. Prior, it was, for the ellipse, it was that a is greater than or equal to b, and that goes away in the case of the hyperbola. The a and the b, they just have to satisfy this equation. Whereas before, it was that b squared is a squared. No, that would mean they're equal. Take away c squared. So a has got to be bigger than b. Very good.